Hello. In today's lecture, we will be talking about the chain rule, generalizing the chain rule to functions of multiple variables. But first, we will think back to Calculus 1 and we will remember how the chain rule worked in one dimension. So the way this worked was you had two functions. You had a function y equals f of x, standard, Calculus 1 function, where y is the dependent variable and x is the independent variable. But then you assumed also an underlying relationship between that independent variable x, which sort of becomes more of an intermediate variable, and an ultimate underlying variable t. And you put them together and you get a composite function y equals f of g of t. And so the idea here is that t is changing, which causes x to change, and because x is changing, y changes. So the question was, how do we compute the derivative of the top level variable y, which depends on x, which depends on t? How do we compute the rate of change of y with respect to t? Okay, so that's what we calculate right here, dy dt. And the way we computed that was to say that it was dy dx, dx dt. Basically, as t changes, that creates a change in x that occurs at a certain rate. And then you multiply that rate of change of x by the rate at which x causes y to change to get the total change rate of change of y with respect to t. This could also be written f prime of g of t times g prime of t, which you have probably remembered as derivative of the outside times the derivative of the inside. All right, and even just a brief example. All right, so our outer function y equals x squared. X, however, depends on sine of t, so the total function is y equals sine of t quantity squared. The derivative dy dt, dy dx, times dx dt. Well, dy dx is 2x, evaluated at x equals sine of t, times the derivative of x with respect to t, which gives us cosine of t, and we get our final answer here, 2 sine t cosine t. All right, now let's extend these ideas to functions of multiple variables. All right, so here's the story. We now have a function, an ultimate dependent variable z, which depends on x and y. All right, but both x and y also depend on t. So the diagram would look more like this. We've got z, which depends on x and y, but both x and y depend on t. So as t changes, it causes x to change, and as t changes, it causes y to change, and both x and y cause z to change. So how do we compute or how do we interpret the rate of change of z with respect to the ultimate underlying variable t? And the easiest way to see this is to draw a picture, as is often the case. So here we have, suppose we have some starting point, and at time t, if you want to think of t as time, it's often helpful, we start at this point right here. And then as t changes, x and y both change, and imagine that this traces out some path in the xy plane. And so after a length of time, delta t, we're now at this position in the xy plane. All right, and as x and y change, z changes. So ultimately, this change in t by an amount delta t creates a change in z of an amount delta z. But to start to understand where the formula for the chain rule comes from, it's easy to, or it's helpful to break this path into two pieces. Ultimately, we start here and we end here, but it's easy to sort of keep track of what's happening if we imagine taking an alternate route, where first we change only x, and we go to the intermediate position here, where we've gotten the x value correct, and then we take another path where we're changing y until we get to the final value. So both of these routes get you to the same point. This is the actual route that was taken as t changes, but this route will help us figure out how much z changed and how to represent it. So now let's start writing some things down mathematically. What is the rate of change of z with respect to t? Well, imagine delta t getting smaller and smaller, as is always the case in a limit. Then what is the total change in z? This change in z along this path is going to be equal to the change in z along this path plus the change in z along this path, assuming the function is continuous. And so we can write that. We can say the total change in z is delta z1 plus delta z2, all divided by delta t, will be our approximation of dz dt. And we can further manipulate this. We can say, well, what is delta z1? Delta z1 over delta t. This change in delta z was caused by changes in x, by the delta x. And so what we're actually going to do is we're going to basically just multiply delta z1 over delta t by 1 in the form of delta x over delta x. And here, because these are deltas, not differentials, we can actually do that. These are actually numbers. They are actually fractions. So when we're in this delta form, we can multiply by delta x over delta x and then rearrange like this. And then over here, the change delta z2 is due to a change in y. So we're going to multiply by 1 in the form delta y over delta y and rearrange. So now we have delta z1 over delta x over delta t, plus delta z2 over delta y over delta t. And this is starting to look like the final result because as delta t goes to 0, this is the definition of the derivative with respect to x. Change in x over change in t as the change in t goes to 0. Similarly, this is the change in y with respect to t as delta t goes to 0. And then these last two, this is change in z with respect to a change in x. Really, delta t is going to 0, but as delta t goes to 0, delta x also goes to 0. So it's also simultaneously the limit as delta x goes to 0. And so this then is the limit of the partial derivative of z with respect to x. So this becomes partial z partial x and partial z partial y. And this is the formula for the chain rule in 2 dimensions. These are partial derivatives because z depends on more than one variable, depends on x and y. So these derivatives with respect to x and y have to be partial derivatives. Whereas because both x and y only depend on the single variable t, those derivatives are full derivatives, denoted with the d. Now, this will be noted later on in this lecture as well, but I do want you to notice that the structure of this form of the chain rule mimics the structure of this little dependency graph that we drew up here. Z depends on x and y, each of which depend on t. You can assign to each edge of this graph a term in the chain rule formula. We have here the dz dx term times dx dt. And here we have the partial z partial y term times dy dt. And so these little tree graphs are very useful for helping you identify the correct form of the partial derivative in any given situation. And in this situation, 2 intermediate variables, 1 underlying variable, you get this formula, which corresponds to this tree graph. So this is what we just said, simply restating this result. If we have two variables, x and y, each of which depend on an underlying variable t, then this is the form of the chain rule in those 2 dimensions. And let's do an example. So don't worry so much about the picture. Well, okay, actually I will talk about the picture. Here's the function of x and y, 2 plus x squared plus y squared. So that's a paraboloid, z equals x squared plus y squared, concave up, and it's elevated 2 units from the xy plane, right? So it's this sort of bowl shape that's been elevated 2 units from the xy plane. And then we imagine that x and y both depend on some underlying variable t. X is 2t, y is t squared plus 3. I have a little note here. This parametric curve in the xy plane, you can actually solve for t and express it as a function y in terms of x, which means you can sort of trace out the curve that x and y are following. So x and y are sort of following this curve down here in the xy plane as t increases. And then you can see that the value of the function f, as x and y trace out this curve, z traces out this curve up here, the red dashed line. X and y are changing like this, and so z is changing like this, and that helps us kind of visualize what's going on with the chain rule. Anyway, now let's just compute it. We have our formula for the chain rule. We can draw our little tree diagram if that helps you. Z, X, Y, T, T. And so the formula is partial f partial x partial t, or dx dt, plus partial f partial y dy dt. And so we plug in what is partial f partial x, that's 2x. What is dx dt? I'm sorry, I can't put them all on the same page. Dx dt is 2, partial f partial y is 2y, and dy dt is 2t. So we're putting all those pieces together here, and if we want, we can then again substitute the expression for x and the expression for y into those expressions to get the rate of change with respect to t. This, I think, you can certainly do this, but if you do this and you substitute everything back to t, you sort of might find yourself asking the question, well, why would I use this formula? Why would I not just first substitute in all the functions of t into x and y and then take an ordinary derivative? But one of the ways that the chain rule is used most often is when you can't necessarily do all that, in which case this expression here gives you the rate of change in this sort of partially simplified form involving x's and t's, which is often sometimes more useful than this final result. If we don't say anything about that here, we'll say something about that in class. Okay, another example could be two underlying derivatives, and this is especially useful in the real world. These two underlying derivatives could be, say, a different coordinate system like r and theta. X depends on r and theta. Y depends on r and theta. That gives you a relationship between Cartesian and polar coordinates. And then say I have a function here, z equals f of x and y, where x and y are both expressed in terms of polar coordinates, and I want to know derivatives with respect to the polar coordinates, not the Cartesian coordinates. All right, so these coordinate changes are an extremely common use of the chain rule. Let's see how that works out. So again, I've got my chart, and I won't sort of try and derive this or anything, but I have my tree chart, z, x, y, but both x and y now depend on underlying variables s and t. And so what is partial z partial s? I have a partial z partial x partial s plus partial z partial y d partial y partial s. And note that now, because x and y both depend on the two variables s and t, these become partial derivatives. So everything contains partial derivatives at this point. So here's all my s derivatives that end in an s, and they are assigned to partial z partial s. Now how do I calculate partial z partial t? Well, I follow my tree chart again, partial z partial x partial t, and partial z partial y partial t. And that gives me the expression for partial z partial t. So let's go ahead and do an example. Suppose I have this function here, z equals e to the x cosine y, and both x and y depend on two underlying variables, t and s. So now I want to compute partial derivatives with z with respect to s. So I have the x derivative of my expression times the s derivative of x plus the y derivative of z plus the s derivative of y for the s derivative of z. And I basically now just compute these partial derivatives. The first line here I've just sort of inserted into the formula without actually taking any derivatives. And then now I can focus on taking the derivatives. That can be helpful to separate these into two stages. So the x derivative of this term is just the term again, e to the x cosine y. The s derivative here is 2. Then what is the y derivative of this? It's negative e to the x sine y. And the s derivative here is just 1. Again, if you like, in these examples, you can simplify here to the underlying variables t and s. And then what is partial z, partial t? It's the same thing. First, I just write out, I insert into the formula the different derivatives in the different expressions. So the x derivative of z plus dx dt plus dz dy dy dt. And then I compute those derivatives, and then I simplify. So really this is just a matter of remembering a couple of formulas, remembering really this tree chart. And indeed, let's talk about the general case. You might encounter problems where there are more than 2 intermediate variables, or where there are more than 2 underlying variables. You might have 4 intermediate with 3 underlying or something, and then you want to know, how do I compute the partial derivative? And really, it's these tree charts again. Okay, so if I have n variables, then I have n terms in my expression, and each one of them, if I'm trying to compute the derivative with respect to some underlying variable ti, then I collect all the terms that end in partial ti, all the way down the line. And then however many variables there are, intermediate variables, that's how many terms appear in the expression. So dz dx1, dx1 dti, dz dx2, dx2 dti, and so on, all the way down the line for the intermediate variables until you get to the end. And then you go to the next underlying variable, and however many of those there are, that's how many lines there are in this list. So here's kind of the illustration of a little more complicated one. 3 variables, 3 intermediates, 2 underlying. W is the dependent variable, depends on x, y, z, and they each depend on st. I can draw this little tree chart. Partial w, partial x, partial s, partial w, partial y, partial s, partial w, partial z, partial s. And that gives me the expression for the derivative with respect to s. It now has 3 terms, 1 for each intermediate variable. Okay, and so you can compute in this way, and so on. I think I'm not going to go all the way through the algebra here in this video. But you do have those notes. You can work through that example, and you should be able to get the same answer as I have. Let's finally turn to one topic for which this is very, very useful and very practically useful, not coordinate changes like I talked about. We'll probably say something about that in class, but implicit differentiation. You had to do this in Calculus 1. And what you were really doing was using sort of a multivariable chain rule, whether you quite realized that or not. And so now we're going to kind of explicitly lay that out, how the chain rule is useful when you're doing implicit differentiation. So again, multivariable calculus, let's now assume, say we've got a function of 3 variables. You might remember an implicit function had a form like this, where you had some function of the variables in the problem equaling 0 or equaling a constant. And this is very similar to level curves, right? Level curves were defined in exactly this way. So an implicit function is really the same as kind of a level curve. So in this kind of formulation, it's not clear, there's not a clear distinction between the dependent variables and the independent variables like there would be in a functional relationship or an explicit relationship. It's not that z is a function of x and y, or x is a function of y and z. You just have this relationship between the 3 variables that has to hold. However, suppose someone says, what is the rate of change of z with respect to x at some point on this surface? This is a surface in 3 dimensions. What is the rate of change of z with respect to x? And you say, well, it's not defined in terms of z, in terms of x. So how do I answer that question? So here's the game we're going to play. Is if you're asked to calculate a partial derivative of one variable with respect to the other, assume that locally on this surface, the first variable depends on the other variables. So for example, we could assume that z depends on x and y. And as long as we're not at some weird point on the surface, locally, this is probably reasonable. All right, we might not be able to describe the whole surface with a single equation of the form z is a function of x and y, but locally we can, right? So for example, say you have a sphere x squared plus y squared plus z squared equals 1. You can't describe that whole sphere with a function of this form, but you can describe the top half in that form, right? So if I'm anywhere on the top half, let's just assume that I can locally describe the function in this way. And what we'll find out is that you don't even have to be able to solve for z to make this work. We just have to assume that it's okay to do that in some vicinity of the point in question. So then suppose this whole example is supposing that they're asking you to compute partial z partial x. So the first step is to say here, assume locally that z depends on the other two variables, and now take the derivative of both sides of the equation with respect to x. So as it says here, this is the key step. If you're asked to compute partial derivatives with respect to x, you take the partial derivative of both sides of this expression with respect to x. And what have we done in here? Very carefully, we've got f of x, y, and then z of x and y. And that's kind of the key step. Because now we can use the chain rule to work out exactly what this is. Of course, the partial derivative with respect to x of 0 is 0. But how do I take the partial derivative of this part in here? Well, I have partial f, partial x, partial x, partial x, partial f, partial y, partial x, and partial f, partial z, partial x. I haven't written down the second term because partial y, partial x, in this local conception, x and y are independent variables, and so they don't change with respect to each other. So that middle term goes away, and these are the only terms that survive. Of course, the rate of change of x with respect to itself is just 1, and so that hangs around. Now I have an expression here equaling 0 containing the very thing it is that I'm trying to solve for. The question was, what is partial z partial x? I don't know, but if I take the x derivative of the function while assuming z depends on x, then out pops a partial z partial x term using the chain rule. And I can now solve for that term, and I get negative partial f partial x over partial f partial z. A couple of caveats. This is only valid, of course, if partial f partial z does not equal 0. And we'll come back to that in a moment. Another thing that's really important is that this example, I love this example because it really highlights the fact that these are not fractions. It's very tempting when we look at a derivative to think of it as a fraction because it has that line with a number above and some symbols below, but they're not actually fractions. If these were fractions, then the partial f's would cancel and you would have partial z over partial x, negative partial z over partial x, which is obviously not the same as partial z partial x. So treating them as if they were fractions in this case gives you completely the wrong answer by a minus sign. They really are whole symbols that need to be thought of together as a unit. Similarly, we can take the partial derivative with respect to y of both sides and get a very similar formula for the partial derivative of z with respect to y. Again, this only is valid assuming that partial f partial z is not 0. The last comment I'll make is not on the page. It's on the next page. Again, I say this all the time, but please don't try and remember this formula. You might forget the minus sign. You might forget which order they go in, which one's on top, which one's on bottom. Really remember this process here that's labeled key step. If someone says implicitly differentiate z with respect to x, z with respect to y, this process is how you do it, and that's the thing you should try and remember. Let's conclude with an example. Again, this is a sphere. This is a sphere of radius square root of 2, and it says compute the rate of change of z with respect to x and the rate of change of z with respect to y at a point on the sphere 1, 0, 1, which is above the x-axis a little ways down the face of the sphere. So, I'm assuming z depends on x and y locally at the point 1, 0, 1. I take the x derivative of both sides to compute partial z partial x. What do I get there? I get 2x plus 0 plus 2z partial x. That goes away, equals 0. I now solve for partial z partial x. I get negative x over z, and I plug in 1, 0, 1, 0, 1, and I get negative 1. Compute partial z partial y. I write down my implicit function. I take the y derivative. I get 0 plus 2y plus 2z partial y equaling 0. I solve for partial z partial y. I get negative y over z. And because y is 0 at the point, I get 0. Here's just a graphical illustration. Here's the point in question. It's always useful to sort of check and make sure that those answers make sense. As x changes, z is indeed decreasing, and so it should be negative. And as y changes, we're walking along the side of the sphere, and z is not changing, and so we should get 0. So now back to this question. What happens if the denominator is 0? Is that really something we need to be concerned about? Well, if partial f partial z is 0, then f is not changing as z changes, which means we're walking along a level curve of the function, the implicit function f equals a constant. And what that means is that the tangent plane at that point is vertical. If my value of f is not changing as z changes, then the surface is tangent to a line in the vertical z direction. That's true on this surface wherever z is 0, and when z is 0, we're on that edge of the sphere that is vertical. And so obviously at those points, it doesn't make any sense to talk about rate of change of one variable of z with respect to the other variables. It's infinite, really, and so it's not surprising that this process breaks down. All right, that's it for this video. We'll see you in class.